Late afternoon, on the 22nd of July, 1944, the Kasumigara Naval Air Technical Training School, roughly 80 kilometers northeast of Tokyo. Lieutenant Commander Minoru Genda stands beside a damaged American fighter, its dark blue fuselage streaked with burns and punctures from 20mm cannon fire. The aircraft had belly landed 2 days earlier. Pilot unconscious, fuel tanks empty. Genda's ground crew had worked through the night to patch holes, fabricate replacement panels from scavenged aluminum, and coax the massive radial engine back to life. Now, the Vought F-4U Corsair sits ready for evaluation, its inverted gull wing casting strange shadows across the tarmac. Genda circles the machine slowly, notebook in hand. He has flown nearly everything in the Imperial Japanese Navy's inventory. He knows the Zero inside and out, understands the Raiden's brutal power delivery, respects the Shiden's temperamental handling. But this American fighter represents something different, something his engineers have been warning him about for months, but he has not yet confronted directly. The technical specifications recovered from the pilot's emergency manual tell an impossible story. 2,000 horsepower at takeoff, 2,400 with water injection for combat emergency, from a single 18-cylinder radial engine displacing 46 liters. Japan's most powerful production fighter engine, the Nakajima Homara, produced 1,900 horsepower on paper, 1,600 in the field with worn components and substandard fuel, and the Homara was proving a maintenance disaster, requiring complete teardowns every 50 hours. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Genda orders the engine start. The propeller swings through compression. Once, twice. Then the Pratt & Whitney R2800 Double Wasp catches with a roar that shakes the ground. Not the high-pitched scream of a Zero Sakai. Not the labored thunder of a Raiden's Kase. This is something else entirely. A deep, sustained bellow of raw mechanical force, the sound of an engine operating well within its design margins, burning fuel with brutal efficiency, converting gasoline into thrust without strain. In that moment, as the Corsair's prop wash kicks dust across the flight line, Genda understands what his superiors have been refusing to accept. The technological gap between Japan and America is not narrowing, it is widening. And nowhere is that gap more visible than in the massive radial engine that now idles before him, its 18 cylinders breathing easily, its exhaust notes steady and confident. This is the story of a test that revealed an unbridgeable divide, of Japanese engineers who examined American engine technology with scientific precision and emerged with conclusions that shattered assumptions, of how one captured fighter exposed the material reality behind Japan's losing war, and of the moment when technical honesty collided with strategic denial at the highest levels of command. To understand what Genda saw in that Corsair, we must first understand where Japanese engine development stood in the summer of 1944. The road to technological defeat began not on the battlefield, but in the design bureaus and testing facilities where Japan's aviation industry struggled to match opponents who operated under entirely different constraints. In 1937, as war clouds gathered over China, Japanese aircraft enjoyed genuine advantages. The Mitsubishi A-5M fighter was faster than anything the Chinese could field. The Nakajima Ki-27 combined speed with the legendary maneuverability that would define Japanese fighter doctrine. Engines like the 900-horsepower Nakajima Sakai and the 1,000-horsepower Mitsubishi Zuisei were reliable, fuel-efficient, and adequately powerful for the missions they supported. Japanese designers had made conscious trade-offs: lightness over protection, maneuverability over firepower, range over ruggedness. These choices reflected both strategic requirements. The vast distances of the Pacific demanded long-range aircraft and industrial constraints. Japan lacked the massive production capacity of Western powers. Better to build many simple, effective fighters than few complex ones. The Sakai engine exemplified this philosophy. 14 cylinders in 2 rows, 27.9 liters of displacement, 940 horsepower at takeoff, dropping to roughly 820 at altitude. It weighed 530 kilograms, remarkably light for its output. The engine ran on 87-octane fuel, required minimal maintenance, and operated reliably for hundreds of hours between major overhauls. Mounted in the Zero fighter, the Sank created a revelation, an aircraft that could escort bombers all the way to Chungking and back, that could turn inside any opponent, that could climb rapidly and fight effectively at 20,000 feet. In the early battles over China, the A6M0 compiled kill ratios exceeding 10 to 1. Japanese pilots became convinced they flew the finest fighter in the world. They were wrong. But the illusion would persist until confronted with overwhelming material evidence. The strategic problem emerged slowly. Japan's war economy produced roughly 7,000 aircraft in 1941. The United States built nearly 20,000 that same year, and American production was just beginning to scale. By 1942, as Japan expanded across the Pacific, American factories delivered 47,000 aircraft. 1943 brought 86,000, and 1944 would see over 90,000 American aircraft roll off assembly lines. The quantitative advantage was crushing, but quantity alone does not explain the Corsair sitting on the tarmac at Kasumigaura. That machine represented a qualitative leap that Japan had failed to anticipate and could not hope to match. American engine development had followed a different path. In the mid-1930s, the United States Army Air Corps issued requirements for fighters capable of exceeding 400 miles per hour. Existing engines could not deliver such performance, so Pratt & Whitney began development of the R2800 Double Wasp in 1936, targeting 2,000 horsepower from an air-cooled radial. The engineering challenges were immense. 2,000 horsepower meant roughly 43.6 horsepower per liter of displacement, a figure that would stress every component. The cylinders would run hot, demanding advanced cooling fin design. The crankshaft would endure tremendous loads, requiring forged steel of exceptional quality. The supercharger would need to maintain boost pressure at altitude while consuming minimal power itself. Pratt & Whitney solved these problems systematically. The cooling fins were machined from solid forgings rather than cast, allowing thinner, more closely spaced fins that dramatically improved heat dissipation. The crankshaft used chrome-nickel steel, heat-treated to precise specifications. The supercharger featured an advanced two-stage design with intercooling between stages to maintain air density. Most critically, every component was designed with margin. The engine could sustain 2,000 horsepower continuously, not just for brief emergency bursts. It ran on 100-octane fuel, but could operate on lower grades with reduced performance. It incorporated sophisticated systems for automatic mixture control, constant speed propeller regulation, and cylinder temperature monitoring. When the R2800 first ran in 1937, it produced 2,000 horsepower, as promised. By 1939, when it entered production, reliability testing had logged hundreds of hours without major failure. And by the time the Corsair entered combat in early 1943, the R2800 was delivering 2,100 horsepower in standard production form, with water injection systems available for emergency power of 2,400 horsepower. Japan had nothing comparable. The closest equivalent, the Nakajima Homar, attempted to match American output from a smaller package, 35.8 liters displacement, 18 cylinders, target output of 1,900 horsepower at sea level, 1,800 at altitude. The Homar represented Nakajima's most ambitious design. It employed technology learned from German advisors and from careful study of American engines. The compression ratio was high, demanding high-octane fuel. The cooling fins were thin and closely spaced. The supercharger used a two-speed drive for better altitude performance. On the test stand, Under ideal conditions, with skilled technicians and premium fuel, prototype Hamaris reached design specifications. In service, they collapsed. The tight tolerances that promised high specific power also meant that any manufacturing defect, any contamination in the lubricating oil, any slight deviation in fuel quality would cause rapid deterioration. Cylinder heads cracked after 30 hours. Pistons seized, bearings failed. By mid-1944, field reports indicated that the average Hummer delivered roughly 1,600 horsepower, not the promised 1,900, and it required complete engine replacement every 50 to 70 hours of operation. Maintenance crews nicknamed it the disaster engine. Pilots learned to nurse failing Hummers back to base, reducing power, babying the throttle, praying the cylinders would hold together long enough to land. The Nakajima Ki-84 Frankfighter, designed around the Hummer, spent as much time grounded for engine repairs as in combat. The material constraints behind this failure were stark. Japan's steel production in 1944 totaled roughly 7 million tons. The United States produced 89 million tons that same year. Japan lacked nickel for heat-resistant alloys, cobalt for high-temperature steel, molybdenum for high-strength forgings. Substitute materials performed adequately in laboratory conditions, but degraded rapidly under combat stress. The human dimension was equally critical. By 1944, Japan's skilled workforce was depleted. Experienced machinists had been conscripted for the army. Precision work fell to hastily trained teenagers and conscripted labor. Quality control, never rigorous by Western standards, effectively disappeared. Engines left factories with improperly torqued bolts, contaminated lubricants, and misaligned components. Meanwhile, American production operated on an entirely different scale with entirely different standards. A single Ford Motor Company plant at Dearborn, Michigan, built more than 57,000 R2800 engines during the war years. Each engine underwent 100 hours of bench testing before installation. Rejection rates for defective components ran below 1%. The supply chain delivered materials of consistent quality, tolerances held within design specifications. This was the context when the damaged Corsair arrived at Kasumigara in July of 1944. Japanese intelligence had reports about the F-4U. They knew it was fast, roughly 410 miles per hour at altitude. They knew it carried 6 50 caliber machine guns with abundant ammunition. They knew American pilots praised its ruggedness and climbing performance. But intelligence reports are abstractions. The machine, now sitting on the tarmac, was concrete. It could be measured, tested, understood. And what Gender's engineers discovered would force uncomfortable conclusions. The recovery of the Corsair had been fortuitous. Lieutenant Edward Roriot's F-4U-1D, Bureau number 82505, had been damaged during a fighter sweep over the Kanto Plain. Japanese records indicate he took cannon fire from a Kai-44 Tojo interceptor. The Corsair's oil cooler was punctured, losing pressure. Roriot, already wounded, attempted to reach the coast, but lost consciousness. The F-4U bellied in near the flight school at roughly 130 miles per hour, sliding 700 yards through a rice paddy before coming to rest. Ground crews reached the wreck within the hour. Roriot was extracted, barely alive. The Corsair, remarkably, was largely intact. The engine had ingested mud and suffered some crankcase damage, but the main structure was solid. Most importantly, the technical documents in the cockpit, including the pilot's handbook and maintenance manual, were recovered undamaged. The Imperial Japanese Navy's First Air Technical Research Arsenal at Yokosuka received the fighter on July 23rd. Commander Toyoda Takago, a designer who worked in the Foreign Technology Program, organized the evaluation team. Roughly 10 officers, 10 civilian designers, and 150 enlisted men were involved in studies of foreign aircraft. The Corsair represented their most significant capture, since an F-6F Hellcat had been recovered from Okinawa the previous October. Takago's team began with external inspection. The Corsair's construction astonished them. The skin panels were thick, far heavier than comparable Japanese designs. Rivet spacing was tight and uniform. The metal showed no signs of warping or poor fit. When they removed inspection panels to examine internal structure, they found massive forgings and heavy-gauge steel fittings. The wing spars were built like bridge girders. One engineer wrote in his notes, "Extremely strong construction. No attempt to minimize weight. Everything is robust, overbuilt by our standards. This aircraft is designed to absorb punishment and continue flying." The landing gear demonstrated the same philosophy. The main struts were 35mm diameter steel, heat-treated to high-strength specifications. The hydraulic actuators were sealed units, protected from contamination. When inspectors removed hydraulic fluid for analysis, they found it clean and properly specified. Even after combat operations and a belly landing, the system showed no degradation. But the true revelation waited in the engine compartment, when the cowling panels came off, exposing the Pratt & Whitney R2808. Even experienced engineers stopped and stared. The radial was massive, 54 inches in diameter at the crankcase, 18 cylinders arranged in 2 rows of 9. Each cylinder head sprouted cooling fins like metal feathers, precisely machined, densely packed. The crankshaft, when extracted for inspection, weighed over 180 kilograms by itself. It was forged from a single billet of chrome nickel steel, heat-treated in multiple stages, then precision ground. The Japanese team photographed it extensively, measuring dimensions, examining the surface finish, marveling at the quality. The cylinder barrels used nitrided steel, a surface treatment that hardened the bore to resist wear while maintaining internal ductility. Japanese engines used cast iron barrels, cheaper but heavier and less durable. The piston rings were chrome-plated for wear resistance. The connecting rods were I-beam forgings, again from chrome nickel steel, each one individually balanced. Every bearing in the engine, from the main crankshaft bearings to the connecting rod bearings to the accessory drive bearings, used precision ground steel races and hardened roller or ball elements. The metallurgical analysis would take weeks, but initial inspection showed material quality far exceeding anything in Japanese production. The supercharger merited its own detailed study, a 2-stage, 2-speed unit driven from the engine's crankshaft through a series of reduction gears. The first stage compressed incoming air, which then passed through an intercooler, a finned heat exchanger cooled by ram air. The second stage compressed it further before delivery to the cylinders. The intercooler was a revelation. Japanese designers knew the principle. Compressed air heats up. Hot air is less dense. Cooling it between compression stages increases final density, meaning more oxygen in each cylinder, meaning more power. But implementing an effective intercooler demanded space, added weight, required complex ducting, and introduced opportunities for air leaks. Most Japanese designs omitted it. The Corsair's intercooler was elegantly integrated into the engine installation. Air from the supercharger flowed through passages in the engine mount structure itself, where cooling fins dissipated heat. The ducting was sealed with gaskets and clamps that could be easily serviced. Temperature sensors monitored the system continuously. It added perhaps 20 kilograms, but recovered that cost by enabling 15% more power at altitude. Commander Takago ordered a complete engine disassembly. Every component was to be photographed, measured, and analyzed. The team worked methodically, documenting everything. 3 weeks later, they had compiled a technical assessment that ran to 140 pages of detailed drawings, specifications, and conclusions. The summary was stark. The Pratt & Whitney R2800 represents an achievement in aircraft engine design that exceeds current Japanese capabilities by a margin of approximately 4 to 5 years of intensive development. The engine delivers 2,100 horsepower at standard military power, with emergency ratings of 2,400 horsepower available through water methanol injection. Comparable Japanese engines deliver 1,600 to 1,800 horsepower in service conditions. Takago catalogued the specific areas where American engineering held decisive advantages. Metallurgy, the chrome nickel steels The nitrided cylinder, barrels, the heat-resistant aluminum alloys used in the crankcase, all represented materials either unavailable in Japan or available only in limited experimental quantities. Manufacturing precision, the tolerances throughout the R2800 were tighter than standard Japanese practice. Surface finishes on bearing races and gear teeth indicated grinding operations beyond current Japanese industrial capacity. The intercooler design was sophisticated but manufacturable with proper tooling. Part 2 of World War II. Script: if you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The system's integration, fuel delivery, ignition timing, propeller control, and supercharger automation all work together through mechanical governors and pneumatic actuators. The level of automatic control reduced pilot workload and ensured the engine operated within safe parameters, even under combat stress. Most troubling was the reliability margin. The R2800 was clearly designed to operate at 2,000 horsepower continuously, not as a brief emergency rating. The components showed evidence of sustained high-power operation without degradation. Japanese engines, by contrast, were designed to barely reach their rated power, with no margin for wear or substandard materials. Takago included a section that would prove prophetic. The philosophical difference between American and Japanese engine design is fundamental. American designers accept greater weight and complexity to achieve reliability and sustained high power output. Japanese designers prioritize lightness and simplicity, but sacrifice durability and power reserves. In prolonged conflict, where attrition matters, the American approach proves superior. But understanding the problem and solving it were entirely different challenges. Takago's report identified what Japan needed: high-grade alloy steels requiring nickel, chromium, and molybdenum, advanced heat treatment facilities with precise temperature control, manufacturing equipment capable of holding tight tolerances, quality control systems to prevent defective components reaching assembly, skilled workers trained in precision machining, and time to integrate all these elements into functioning production systems. Japan had none of these things in sufficient quantity, and by July of 1944, time had run out. The report reached Vice Admiral Takejiro Onishi, commander of the 1st Air Fleet, in early August. Onishi read it twice, then called a conference of senior technical staff. The meeting took place on August 9th at the Navy Ministry Building in Tokyo. Besides Onishi, the room included Commander Takago, Lieutenant Commander Genda, representatives from Nakajima and Mitsubishi, and several staff officers responsible for aircraft procurement. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Takago presented his findings in person. He spoke for roughly an hour, methodically working through the technical analysis. He showed photographs of the R2800's components. He presented comparison tables of Japanese versus American specifications. He explained the metallurgical requirements and the manufacturing challenges. When he reached his conclusions about the 4 to 5 year technology gap, the room fell silent. Everyone present understood what this meant. Japan was not merely behind in engine technology. The gap was widening, not closing, and with American bomber raids intensifying, with industrial capacity hemorrhaging, there was no realistic path to catch up. Admiral Onishi asked the question everyone was thinking: can we copy the American design, build our own version of this engine? Takago's answer was carefully worded, but unambiguous. Theoretically, Admiral, yes, we understand the principles. We have detailed measurements and drawings, but practical implementation faces insurmountable obstacles. The steel alloys require imported materials we no longer have access to. The manufacturing precision demands machine tools we cannot build quickly enough. Even if we secured materials and tooling tomorrow, training workers and establishing quality control would require at least 3 years. And we would still face fuel quality issues. The R2800 is designed for 100-octane gasoline. We have 92 octane at best, often lower. A representative from Nakajima, Chief Engineer Takeo Doi, proposed an alternative. What if we focus on improving existing designs rather than attempting to copy American engines? The Homar has fundamental soundness. Its problems are manufacturing and materials quality. With better steel and stricter quality control, it might approach design specifications. Takako nodded. That is more realistic. But it addresses symptoms, not causes. Even a perfectly manufactured Homar with premium materials delivers 1900 horsepower. The American engine delivers 2400. And their next-generation engines, we have intelligence suggesting they are testing units producing 2800 horsepower. We are not closing the gap. We are falling further behind. The discussion turned to alternatives. Could Japan develop its own advanced engines, learning from, but not directly copying American designs? Could different approaches, more compact engines, liquid-cooled designs, even early turbojets, offer shortcuts around the material limitations? Each proposal met hard realities. Development required time measured in years. Testing demanded resources that were being consumed by daily attrition. Production needed industrial capacity that was being systematically destroyed by B-29 raids. And underlying everything was the material deficit. Without high-quality steel, without precision machine tools, without skilled workers, Japanese engines would continue underperforming. Lieutenant Commander Genda, who had flown the captured Corsair by then, offered a pilot's perspective. The performance difference is even more dramatic in the air than on paper. The Corsair accelerates like nothing we have. It climbs at over 3,000 feet per minute. At altitude, where our fighters struggle, it remains responsive and fast, and the pilot sits behind armor plate in a reinforced cockpit. Our pilots fly fighters made of wood and fabric, unarmored, knowing any hit could be fatal. The psychological effect is considerable. Genda's flight test had occurred on August 5th. Engineers had repaired the damaged Corsair sufficiently for cautious evaluation. Genda performed 3 flights, totaling roughly 2 hours of airtime. He explored the aircraft's handling characteristics, tested the control responses, pushed the speed up to 350 miles per hour, and attempted mock combat maneuvers. His written report described the experience with clinical precision. Takeoff requires attention to torque, but is straightforward. The engine delivers smooth power. Climb rate is exceptional. Roughly 3,200 feet per minute at sea level, the aircraft feels heavy but responsive. Control forces are moderate, heavier than a Zero but lighter than a Raiden. At altitude, the Corsair's advantages become overwhelming. Above 6,000 meters, where Japanese fighters begin losing performance, the Corsair remains strong. The supercharger maintains power. Speed stays high. In mock pursuit of imaginary opponents, I could maintain or increase speed in climbs, something impossible in our fighters. The combat radius implications are severe. With drop tanks, the Corsair has sufficient fuel for over 2 hours of combat operations at extended range. Our fighters must conserve fuel carefully. The Zero can match the Corsair's range, but not its performance. The Raiden has performance, but not range. The Corsair provides both. Genda's conclusion was blunt. In combat, between a well-flown Corsair and any Japanese fighter currently in service, the American pilot holds every advantage except turning radius. He is faster, climbs better, has more firepower, and sits protected behind armor. If he chooses to fight, he will likely win. If he chooses to disengage, we cannot catch him. This aircraft represents the future of fighter aviation. We are flying relics of the past. Admiral Onishi read these reports with the expression of a man watching his worst fears confirmed. He had commanded naval aviation throughout the war. He had seen Japanese air power decline from dominance to desperation. He had watched skilled pilots replaced by hastily trained boys. He had ordered attacks knowing most would not return. And now, The technical assessment proved what battlefield experience had been teaching. Japan had lost the technological race decisively. But Onishi faced a dilemma. As a senior commander, he could not publicly admit defeat. Military culture demanded confidence, aggressive spirit, willingness to overcome any obstacle through fighting spirit. Technical reality might say the war was lost, but duty required fighting on until ordered to stop. In private, Onishi was more honest. In a conversation with his chief of staff recorded in post-war interviews, he spoke frankly. The Corsair is merely one example. The Hellcat is similar, the Thunderbolt even more formidable with its turbocharger. Every month, American aircraft arrive with better performance. Ours decline as materials degrade and skilled workers disappear. We are bleeding experienced pilots at an unsustainable rate. New pilots lack training time because we lack fuel and aircraft. The mathematics are merciless. The chief of staff asked what could be done. Onishi's answer was fatalistic. We fight, we die. We hope our deaths purchase something valuable. Perhaps they delay American advances long enough for negotiation. Perhaps they demonstrate resolve that influences peace terms. But we do not win. The material disparity is too great. This was August of 1944. Japan would fight for another year. Another million would die. But for those who examined the Corsair at Kasumigara and understood what it represented, the outcome was already determined. The captured F-4U was not the only American aircraft Japanese technical intelligence evaluated. Throughout 1944 and into 1945, other types were recovered and studied. An F-6F Hellcat from Okinawa in October of 44, a TBM Avenger from the Netherlands East Indies, a P-51 Mustang that force-landed in Japan itself, even a B-17 Flying Fortress patched together from multiple wrecks and flown by Japanese pilots. Each evaluation told the same story. American aircraft were heavier, more rugged, more powerful, and more reliable than Japanese equivalents. The metallurgy was superior. The manufacturing quality was higher. The systems integration was more sophisticated, and the performance margins were greater. Japanese engineers compiled these findings into comprehensive reports. They documented the technology gaps. They proposed solutions, better materials, improved manufacturing, advanced designs. But the proposals were academic exercises. The resources to implement them did not exist and could not be created in the time available. Some engineers saw this clearly and adjusted their focus. Instead of trying to match American performance, they designed for what Japanese industry could actually build. The result was aircraft, like the Kai-100 fighter, which mated an older, reliable Mitsubishi Kinsei engine to the Kai-61 airframe. The Kai-100 was not as fast as a Corsair. It could not climb as quickly, but it was reliable, manufacturable with available materials, and effective enough in skilled hands. Others doubled down on technology. Japan could still leverage. Maneuverability remained a Japanese strength. Lightweight. Construction allowed tight turning. Experienced pilots in nimble fighters could still threaten heavier American aircraft in close combat. This thinking led to aircraft like the Kai-84 Frank and the N1K2 Shinkai, fighters that prioritized agility over armor and firepower over protection. But these were stopgaps, not solutions. American pilots learned to avoid turning fights. They used their speed and climb advantages to control engagement geometry. They attacked from altitude, made a single high-speed pass, and escaped before Japanese fighters could respond. The famous thatch-weave tactic allowed two American fighters to cover each other, eliminating the vulnerability of a single aircraft in a turn fight. And the numbers kept grinding forward. In August of 1944, American factories produced 7,400 aircraft. Japan produced 1,500. The kill ratios in air combat, once massively favoring Japan, had reversed. American pilots achieved 2-to-1, sometimes 3-to-1 exchange rates. Japanese losses were unsustainable. American losses were rounding errors in the monthly production totals. The Corsair that landed at Kasumigara flew again only once more under Japanese markings. On August 23rd, Commander Takago conducted a final evaluation flight. He took the F-4U to 15,000 feet, ran it through a series of maneuvers, then landed. The engine was showing signs of wear from running on low-grade Japanese fuel and inadequate maintenance. Cylinder head temperatures were erratic. Oil pressure was dropping. Rather than risk catastrophic failure, Chicago grounded the aircraft. The Corsair sat on the tarmac through the autumn as Japan's situation deteriorated. The Philippines fell. B-29 raids intensified. Iwo Jima was invaded in February of 1945, Okinawa in April, and on August 6th, the atomic bomb fell on Hiroshima. 3 days later, Nagasaki. On August 15th, the Emperor announced surrender. American occupation forces arrived at Kasumigara in early September. They found the captured Corsair still there, now surrounded by wreckage from air raids that had devastated the facility in the final months of the war. The F-4U was photographed extensively, examined by American technical intelligence, then scrapped. Its service to aviation history was complete. Commander Toyoda Takago survived the war and was interviewed extensively by American intelligence officers. His reports on captured Allied aircraft were considered among the most thorough and objective produced by any combatant. In post-war questioning, he was asked why Japanese evaluations had been so honest about American technical superiority. His answer was simple. We were engineers, not politicians. Our duty was to provide accurate technical assessment so commanders could make informed decisions. We documented what we found. The materials were superior. The manufacturing was better. The performance was higher. These were facts, not opinions. Hiding them would have served no purpose. But Takago acknowledged the findings had little impact on strategy or operations. By 1944, Japan's course was set. We lacked the resources to close the technology gap. We lacked the time to develop new approaches. We lacked the industrial capacity to implement changes. The evaluations documented our defeat. They did not prevent it. Lieutenant Commander Genda, the pilot who flew the Corsair, also survived and had a distinguished post-war career, eventually rising to become Chief of Staff of the Japan Air Self-Defense Force. In interviews decades later, he reflected on that flight in August of 1944. Flying the Corsair was like looking into the future. Everything about it spoke of industrial might and technical sophistication. The engine ran so smoothly, the systems worked so reliably, the controls felt solid and confident. I thought about our pilots, flying fighters with half the power, no armor, unreliable engines, knowing they faced aircraft like this. It required tremendous courage, or perhaps it required not fully understanding the odds. Genda was asked if the Corsair flight changed his view of the war. It confirmed what I already suspected. We were not going to win through superior technology or industrial capacity. Our only hope had been to strike early, inflict maximum damage, and negotiate from a position of temporary strength. But we had failed to achieve decisive victory in 1941 and 42. By 44, the material imbalance was fatal. The Corsair was simply one very visible manifestation of that imbalance. The R2800 engine that powered that captured Corsair represented more than just superior horsepower. It embodied a completely different approach to engineering and manufacturing. American designers built in margin, accepting extra weight for reliability and sustained performance. American factories emphasized quality control, rejecting imperfect components, even if it slowed production. American metallurgy provided materials that maintained properties under stress, and the American economy supported all of this with resources Japan simply could not match. By the war's end, over 125,000 R2800 engines had been produced by Pratt & Whitney and its licensees. They powered not just the Corsair, but the Hellcat, the Thunderbolt, the Black Widow night fighter, the B-26 Marauder bomber, and numerous other types. The engine served into the 1960s in some applications. Its reliability became legendary. Japan's Nakajima Homar, by contrast, was produced in quantities around 18,000 units. It powered the Ki-84 Frankfighter, the B-6N Tenzan torpedo bomber, and a few other types. Its unreliability became equally legendary. Mechanics cursed it, pilots feared it, and when Japan transitioned to post-war aircraft development, the Homar design was abandoned completely in favor of licensed American engines. The story of the captured Corsair is ultimately not about one fighter or one engine. It is about the collision between industrial realities and military necessity. Japan entered the war knowing it faced material disadvantages. Japanese planners counted on superior training, better tactics, and fighting spirit to compensate. For a brief period in 1941 and early 42, when Japanese pilots were experienced and American forces were unprepared, that calculation seemed to work. But war is ultimately a contest of industrial capacity and technological sophistication. The side that can produce more aircraft with better performance and replace losses faster will prevail if all other factors are remotely equal. By 1944, all other factors were not equal. American pilots were well trained, American tactics were refined, and American industrial capacity was overwhelming. The Corsair at Kasumigara was simply one data point in a comprehensive pattern. Japanese engineers examined it, documented its superiority, and reported their findings to commanders who could do nothing with the information. The war continued because honor demanded it, because surrender was unthinkable, because the institutional momentum of a massive conflict could not be stopped by technical assessments. But the engineers knew. They knew in July of 1944, when they measured the R-2800's components. They knew when they calculated the power-to-weight ratios. They knew when they analyzed the metallurgy. They knew when they read Gender's flight test report. They knew the war was lost, even if that knowledge could not be spoken openly. In the decades after the war, aviation historians debated what might have happened if Japan had made different technical decisions. What if Japanese designers had prioritized engine development over airframe refinement? What if industrial resources had been concentrated on fewer, better designs instead of scattered across many mediocre ones? What if Japan had copied German jet technology earlier or focused on high-altitude interceptors for homeland defense? These questions are counterfactuals without clear answers. But the captured Corsair suggests the fundamental problem was not design choices or strategic priorities. It was material capacity. American industry produced the steel, aluminum, and alloys that Japanese industry could not. American factories maintained quality standards that Japanese factories could not sustain. American workers possessed skills that Japanese workers, often conscripted teenagers, had not developed. Technology gaps can be closed with sufficient resources and time. Japan lacked both. The 4 to 5 year estimate in Takago's report assumed Japan could obtain necessary materials, train adequate workforce, and establish quality manufacturing processes. But Japan was being bombed, blockaded, and systematically dismantled. The 4 to 5 years might as well have been 40. Admiral Onishi, who read the Corsair evaluation in August of 1944, would later organize the first systematic kamikaze attacks in October of that year. The logic was brutal, but consistent with the material realities he understood. If Japanese aircraft could not defeat American fighters in combat, and if Japanese pilots lacked the training and experience to survive prolonged engagements, then perhaps suicide attacks bypassing conventional combat could inflict losses that mattered. The kamikaze campaign killed thousands of American sailors and damaged hundreds of ships, but it did not alter the war's trajectory. It simply consumed Japan's remaining pilots in suicide missions that achieved tactical damage while surrendering any hope of recovering air superiority. Onishi knew this, but by autumn of 1944, no good options remained. Only choices between different forms of inevitable defeat. The engineers at Yokosuka who examined the Corsair understood this months before Onishi organized the Kamikaze Corps. They saw it in the precision of American manufacturing. They measured it in the specifications of American engines. They calculated it in the performance margins that separated the R-2800 from the Homar. And they documented it in reports that remain in archives today, technical epitaphs for a lost war written by men who knew the truth but could not change it. Today, more than 80 years after that Corsair belly landed near Kasumigara, we can examine the historical record with dispassion that was impossible in 1944. The technical assessments were accurate. The Pratt & Whitney R-2800 was indeed a superior engine. The manufacturing quality was indeed higher. The material advantages were indeed decisive, but the deeper lessons about how technological competition unfolds in wartime. Development cycles that take years cannot be compressed by urgency alone. Manufacturing infrastructure cannot be created overnight. Skilled workforces cannot be trained in months, and material deficiencies cannot be overcome by fighting spirit, no matter how intense. The Japanese engineers who examined the Corsair did their duty. They documented reality accurately. They provided honest assessment to commanders, and they watched as that reality unfolded exactly as their analysis predicted, not because commanders ignored their findings, but because the findings described a situation beyond Japan's power to change. The Corsair flew away from that encounter, symbolically at least, to continue dominating Pacific skies for another year. The Japanese engineers returned to their design bureaus to continue working on aircraft they knew were obsolete before completion, and the war ground forward to its inevitable conclusion, delayed by courage and sacrifice, but ultimately determined by the material factors that captured Corsair represented so completely. When the surrender came in August of 1945, few were surprised who had examined the technical evidence. They had known since July of the previous year, since the moment they measured the R-2800 cylinder barrels and calculated the power output and understood what it meant. The war was over then. It just took another year and another million deaths for the fighting to stop. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.